Everyone, my name is Ritesh Pandey, and in this video we'll talk about a very popular and a very peculiar reduction process called Birch reduction. Now you would either see Birch reduction in the reduction of an aromatic compound like benzene, or you would see Birch reduction in the reduction of an alkyne to an alkene. It's a very specific process where alkyne will stop at alkene and the alkene produced will be always a trans alkene. So it's a very specific, very peculiar reduction process. Even for benzene, you would see the product would be a non-conjugated diene. So I repeat, it's a very specific process. We are going to talk about the mechanism and all possible variations of Birch reduction. In the sense, I have put up all possible questions, all variations of Birch reduction which can come in any entrance exam. In the beginning of video, you can either take a snapshot of this or you can pause the video, you can copy down all of them. If you have read about Birch reduction, you can try these questions of your own. Chances are nothing beyond will come in any exam at your level. And once you have tried these questions, you will want to see the video. In this video, I'll be talking about the mechanism and solve all of these questions one by one. So let's begin with the first reduction involving benzene, and the reagent, I repeat, is lithium or sodium in liquid ammonia with or without alcohol. You'll want to first of all copy down all of it, and I'm going to solve these questions one by one. Now naturally, the first question is benzene, and I told you the product is a very specific non-conjugated diene. It's a non-conjugated diene. You get a non-conjugated diene. The reagent lithium or sodium is a very reactive alkali metal. It will lose electron. Ammonia would be the solvent. In absence of alcohol, it will play the dual role of a solvent as well as proton donor. If suppose an alcohol is present here, this will be the proton donor and the process can be conducted at a lower temperature. You know, OH bond is more polar than NH because oxygen is more electronegative. Now what is the mechanism? A possible mechanism is, we'll begin with lithium or sodium. Lithium or sodium, naturally being very reactive, will lose its electron, and this electron will go to the ring. This electron will go to the ring. Now suppose this electron goes to this carbon and the pi bond comes here. Naturally this will be the first intermediate. You will have a single electron coming here and this pi bond becoming a lone pair. You should be good at drawing resonating structures. These are, say, the resonating structures. This will be the next resonating structure, negative here and this dot here. And say this is the third resonating structure where this pi bond can come here and this will again go here. Now, if there are three resonating structures, say A, B and C, or I'll call it 1, 2 and 3. Naturally 1 and 3 will look similar, 1 and 3 will look similar. 2 is different in the sense, in 2, the single electron and the lone pair are at maximum distance. They are like para positions. 1 and 3 will look similar. It's very important to know the mechanism and know this intermediate. First of all, this intermediate is called a radical anion. This intermediate is called a radical anion. You will want to relate to this name. The way for a single electron you use the term free radical, it's radical and then a carbanion ka anion as well. Now out of these three intermediates, naturally 2 will appear the most stable. 2 will appear the most stable because here the distance between these two is maximum. Here the distance between these two is maximum and the repulsion is minimum. Here the distance between these two is maximum, the repulsion is minimum. So out of these three, 2 is suppose the most stable radical anion. And it's important to know that यहाँ पे the separation is maximum, repulsion is minimum, this is most stable because this will mature to the final product. Had 1 and 2 mature to the final product, you would have got a conjugated diene. See, double single double is conjugated, double single double is conjugated. But you know the product is non-conjugated, the product looks like this, double single single double. So you need to understand the nature of the intermediate, the stability of this form of this intermediate where these two are at maximum separation, minimum repulsion, and then we'll want to carry on with this form of the intermediate. More molecules will form this intermediate because this is more stable, and naturally now ammonia acting as a solvent or alcohol acting as the proton donor. In absence of alcohol, this can also donate hydrogen. This H plus will come here, this H plus will come here, and it would give you hydrogen here, it would give you hydrogen here. Another mole of lithium or sodium losing another electron, this can lose another electron, and if this electron comes here, if this electron comes here, you know, you'll have a negative charge here, and again ammonia or alcohol can provide this hydrogen, ammonia or alcohol can provide this hydrogen, and it will get this hydrogen. So you're getting a hydrogen out here, you're getting a hydrogen out here, basically you're getting a hydrogen here, you're getting a hydrogen here. I told you in presence of alcohol, alcohol will be the proton donor, otherwise ammonia can donate hydrogen. You see the two hydrogen coming at the two para positions, which are also like positions 1, 2, 3 and 4. So many times Birch reduction is very popularly called, it's very popularly called a case of 1,4 addition. Now all this information will be very handy in solving questions of different types. So many times you have matrix match questions where you need to know about all mechanisms which are 1,4 addition. I repeat, you call it 1,4 addition. You call it 1,4 addition because you find the two hydrogen atoms added at position 1 and 4. So before everything, you will want to write this mechanism. We'll begin with lithium or sodium losing an electron coming here, a radical anion formed out of 3 intermediates. You will want to draw them of your own. This is the most stable one. So this will mature to the product. Here it will gain a hydrogen from the proton donor. Then again a single electron from lithium or sodium. Very reactive alkali metal would give you a negative charge here. It can again catch H plus, form the final product. The final product is non-conjugated because it's coming from the corresponding radical anion, which is again non-conjugated in nature. Conjugated is more stable than non-conjugated. So you know that is the peculiarity, that is the significance of this reduction. That from a very stable aromatic compound, you are able to produce a relatively less stable non-conjugated diene. So this is how we'll want to begin with one proper mechanism understood, and then I'll be taking up all the variations. In the sense, you would have copied down all the questions. We'll be solving all examples one by one, but trust me, this information will come handy while solving all variations of Birch reduction. Once you are done with this, we'll talk about the example 2 and example 3, which were naphthalene and anthracene. Example 4 onwards, you know, when you have a group attached to the ring, if you have copied, question 4 was anisole, question 5 was benzoic acid, having a plus R or a minus R effect, you know, there's this information, this mechanism will be very useful. You'll want to copy down this, and then I'll move to question 2. Now, expecting this is understood, we'll move to question 2 and question 3, which are aromatic compounds only. Again, very simple applications, and you would have known these compounds from aromaticity. So if it is naphthalene, the product of Birch reduction would be, so this is the aromatic ring and this would be non-conjugated. So if I draw it in this way, you know, this ring will look non-conjugated, double, single, single, double, double, single, single, double. So this will be the product of naphthalene Birch reduction, where one ring will get reduced. Naturally, whether you write it in this form or you write it in this form, the two are identical. You know, the two are identical. You can write either this form or this form. Both are same. That is the case with naphthalene. With 3 rings, which is anthracene, you will always find the middle ring. Out of these 3 rings in anthracene, you will always find the middle ring is the most reactive one. And chances are this will be the final product. Where these two aromatic rings will be retained. There is a basic fact behind it. The logic is 2 benzene rings, and generally it's taught in aromaticity. 2 benzene rings have more stability than one naphthalene. You know, another possibility could have been, you know, you could have drawn two rings of this kind and a pi bond here, you know, that would not look good. That would not look good, because between two back-to-back rings, between naphthalene and 2-benzene, you would learn this in aromaticity, 2 benzene rings have more stability, more resonance energy than a naphthalene. So something of this kind does not happen, and every time in anthracene, to get 2 benzene rings, oxidation and reduction both will happen at the middle ring. Oxidation and reduction both will happen at the middle ring. Hamesha middle ring is subjected to oxidation reduction, so that 2 aromatic rings or 2 benzene rings are always retained. Here again, if you look at the middle ring, you will find it non-conjugated, double, single, single, double. So the middle ring has been reduced and the product is a non-conjugated diene in one way. Now, after noting down example 2 and 3, we'll want to talk about example 4, 5, 6 and 7, which I repeat are very, very popular cases. The mechanism is not very clearly given in most of the popular textbooks, and this is where this video becomes even more significant. Example 4 is when you have OCH3. First of all, this compound is called anisole, and we need to understand that OCH3 is a plus R group, Plus R means electron repelling group. You have the lone pair, which keeps the ortho and para positions electron rich. So again, this is taught in electrophilic substitution, this is taught in basic aromaticity. A plus R group with a lone pair, with at least one lone pair, will keep ortho and para positions electron rich. What if this compound undergoes Birch reduction? Now you will see this with sodium in liquid ammonia or lithium in liquid ammonia, which is Birch reduction. And there are two possibilities. Previously, there was no attachment, all carbon atoms were equal. Now, with a group attached to the ring, you can either have a product like this, or you can have a product like this. See, the difference is both are non-conjugated, both are diene, but this happens to be a non-conjugated diene where the carbon bearing the pi bond is the carbon having the group as well. Or in other words, the carbon to which OCH3 is attached, that carbon bears the pi bond as well. Whereas here the carbon having OCH3 group does not bear the pi bond. Naturally, these two are isomers. These two are two different compounds, and the first information you will want to have is between these two, this would be the major product, this would be the major product. That would not happen. This would be the major product, and I'll need to explain this. In the sense, if you have a plus R group attached, you will always have a product, such that the carbon bearing the group will also bear the pi bond. Question 5, by the way, is benzoic acid, where you again know COOH has a prominent minus R effect. It has a minus R effect, it's a minus R group, it's electron withdrawing group. And before everything, I'll tell you that this minus R group, when it's subjected to Birch reduction, again there are two possibilities. Either this or this is possible. Where either it's sharing the pi bond along with the group, or the carbon bearing the group is not sharing the pi bond. When it's a minus R effect, the reverse will happen. This would be the product, this would be the final product formed. The previous one is not seen, this is going to be the final product. So before everything, you will want to know the result, because so many times in the real exam, they'll only want the result. In the real exam, they'll only want the result. The mechanism is not very clearly given in most of the sources. So you'll want to know the mechanism only for value addition. Just in case there's a question on the mechanism, you'll want to know it. I'm going to talk about it, but otherwise, you'll need to know the result first. If it's a plus R group, electron repelling group, you'll want to draw a non-conjugated diene where the carbon bearing the group also bears the pi bond. Whereas if it's a minus R effect, the carbon bearing the group will not bear the pi bond. So these are the results which you'll want to know, and then we can talk about the mechanism. Now the reason you have the corresponding products is the fact a plus R group is ortho-para orienting. A plus R group is ortho-para orienting. Plus R में Naturally, ortho and para positions are electron rich. You will want to listen very carefully. Ortho para positions are electron rich in plus R group. A plus R group, ortho para positions are already electron rich. Plus R group, ortho and para positions are electron rich. Now suppose if I start the same process, lithium or sodium losing its electron and this electron, now because there is a branching here now, a grouping here, there are two possibilities. It can go either to this carbon and this can come here. See, in that case, this will be the corresponding radical anion, this will be the corresponding radical anion. The other possibility is this electron instead going to this carbon, and in that case the pi bond will come here. Suppose I call it possibility A, I'll call it possibility A, so that the negative coming at the ortho position is possibility A as the intermediate, and if we call it possibility B, where you understand the electron is going to the ortho position and this lone pair is coming to the carbon having OCS3, this is possibility B. So if this is possibility B, I'll call this intermediate B, and because this will not mature to the final product, the one which will mature to the final product is when these two are at maximum separation. We'll want to write the corresponding resonating structure. So for this, for possibility A, this is the radical anion in contention, this is the radical anion in contention, where suppose this lone pair comes here, and certainly the resonating structure for this one, where again I'll want to have these two at maximum separation, I'll want to pull it down here so that it comes here, and naturally it will look like the following. This time you will want to have a pi bond here, a lone pair here, negative, and this would be the intermediate. Now it's either this intermediate or this intermediate which will mature to the final product, because right a few minutes back I told you when they are at maximum separation at the para position, you know, that is the intermediate which matures to the final product. So you have to choose between either this or this. You know, this is when possibility A is happening, this is when possibility B is happening. Now you again go back to the initial information. OCS3 plus R has already kept ortho and para positions electron rich. यहाँ पर पहले से ortho para position electron rich है. So whether this or this, you know, where ortho and para are getting more negative charge is not favored because ortho and para positions without this mechanism, because ortho and para positions are already electron rich. I want to emphasize plus R group is one where ortho and para positions are electron rich. They are electron rich, they are high on electron density. So a mechanism where more negative goes to the ortho and para position is not preferred, is not favored. Because ortho para पे पहले से electron density ज़्यादा है, more negative at ortho and para is not favored because the ortho and para are already electron rich. A negative charge developing there would rather cause repulsion. So A is not favored. You will want the negative to go to meta where there is not an excess of negative charge or electron density. B will be preferred, and certainly if B is preferred, if this is not going to happen, if B is preferred, you will want to try it of your own, you will want to draw the structures of your own. This would be the final product, Now you understand whether you write it in this form or you write it in this form, it means the same. So naturally you write it in this form or you write it in this form, you know, these two are same. Basically the product is the one where the carbon bearing the group, also bears the pi bond. So this is how you will be able to explain for a plus R group. Naturally exact reverse will happen with a minus R group. I repeat, I have given you a mechanism. I have told you out of two possibilities A and B, because this is keeping ortho and para position electron rich. It's keeping ortho and para position electron rich. A possibility जहाँ पे ortho और para पर और negative charge जाएगा would not be favored. वहाँ पे पहले electron density ज़्यादा है. A more negative there will be repelled. You know, it will cause repulsion. It will not be favored. A process where, you know, the negative goes to the meta position instead, you know, would be preferred, and the product, the result would be eventually the product, the non-conjugated diene would be such that the carbon bearing OCS3 will bear the pi bond as well. The exact reverse is expected. If instead of OCS3 you have a COOH here. I'll clear this area, or maybe, you know, I'll want to draw it all over again. In example 5, which was benzoic acid, in example 5, which was benzoic acid, which you know is a very popular minus R effect. Now what is minus R effect? What is minus R effect? Minus R effect is electron withdrawing effect. And this time there is electron deficiency at ortho and para position. So this is what is happening by default. By default, ortho and para positions are electron deficient. So in this case, when the reagent will approach, or lithium or sodium will approach, losing its electron, and this electron either goes again to, again I'll talk about possibility A, producing say an intermediate A, and possibility B, producing an intermediate B. So if it goes instead to this ortho position, naturally this pi bond would have come here, and this would be possibility B. This is negative here, and I'll draw the resonating structure, because this will decide the final product. This will decide the final product. Here the negative and the lone pair are at maximum separation. This will cause the 1,4 addition. And if I do the same here, you will want to try it of your own. You will want to draw these of your own. Naturally, this time, because it's the ortho and para positions which are electron deficient. Minus R effect means ortho and para are electron deficient. Ortho and para पे electron deficiency है. So a possibility where the electron deficiency will be cured. यहाँ पर ortho para पे electron density कम है. So a possibility where negative comes at ortho and para positions will be welcome. So out of these two possibilities, A and B, naturally this time A will be preferred, because at ortho and para position you have electron deficiency. You would want to know a little bit about minus R meta orienting effect before coming till this point. And naturally, because ortho para electron deficiency यहाँ पर there the negative charge would facilitate the mechanism. Electron deficiency है, a process where ortho and para get electron rich will be preferred. A would be more likely this would not happen, and this will certainly mature to a product which will be non-conjugated dyne, such that the carbon bearing COOH does not bear the pi bond. So these are results which I had told you 10 minutes back. Plus R effect, hyperconjugation effect, repelling effect, and the carbon bearing the group will bear the pi bond as well. Minus R effect, carbon bearing the group will not bear the pi bond. So although you need to know the results more often than not, this is going to make the picture very clear. And the rest of the examples are going to be pretty simple. Now after these cases, there were a couple of examples where certainly one was toluene. Now when it's toluene, where you have CF3 hyperconjugation, which is same as a plus R. Naturally here, Birch reduction, if it's plus R, you know the result. It will be there with the carbon bearing the CF3, and certainly if it's cyanobenzene, which is minus R, the product would be such that the carbon bearing this group will not get this pi bond. Something very similar will be expected with even a group which is NO2, a very popular minus R group, and this will be the final product. So henceforth, the cases are going to look simple. It's all explained in the mechanism which I told you. Here, a plus R or a hyperconjugation or a repelling group, carbon bearing the group will share the pi bond. Minus R effect, carbon bearing the group will not get the pi bond. So I think all of this will be very clearly understood now. We'll talk about the rest of the examples. Question 8, I believe, was a case where you had two rings with one having CH3 and another one, the next one was one having NO2. Now this is plus, hyperconjugation is like plus R, so hyperconjugation is electron repelling, and this NO2 is minus R. So minus R will make this ring electron deficient. This will make this ring electron rich. Naturally, the ring which is electron rich, again this is very basic logic. ये रिंग अगर इलेक्ट्रॉन रिच है, ये रिंग अगर इलेक्ट्रॉन रिच है, this would gain the electron, and if this gains electron, expect reduction of this group. The one bearing CH3 will not reduce, the other one will get reduced. अगर ये माइनस आर है, this is electron deficient, इसको इलेक्ट्रॉन चाहिए, this will take electron, this will get reduced, and if this gets reduced, naturally this ring will get reduced. Non-conjugated, double, single, single, double, double, single, single, double. So I hope again this is very logically understood. ये methyl का plus hyper conjugation है, electron repelling nature है, so this ring is electron rich. Electron rich will not get electron, this will get electron, so this ring gets reduced. Here this ring is electron deficient, so the one which is having minus R being electron deficient will get the electron, will get reduced. So all these would be looking very obvious if you apply some logic. Last two problems, 10 and 11, and because it's a very popular reduction mechanism, even for alkyne, you are taught that Birch reduction will always give you a transalkene. It will always give you a transalkene. See, this is trans. A very specific mechanism, it will always produce a transalkene. This I believe was the last one. Cyclodecane, you know, if you draw it in this way, and you place a pi bond here, or you place a pi bond here, basically these four are positions where a pi bond placed would give you a transalkene. It goes down, it goes up, it goes down, it goes up. You know, this is transcyclodecene. I can give you a cis product. You know, this is a cis product. A pi bond here would look cis, a pi bond here would look cis, but that will not happen. It will give you a transalkene. This will not be formed. Cis नहीं बनेगा, trans बनेगा, normal alkyno. The one in question was, I believe, involving CH3. It was butane, I believe. It was butane, so this will be the product. Trans to butene. And again, the mechanism has to be very simple. See, you know, you'll want to copy this, and in a minute I'll be able to explain this to you. See, when lithium or sodium, after losing its electron, you know, if it attaches itself to this carbon, this pi bond will always go in a manner, this will always go in a manner, so that this is at transposition to this. It's a transposition to this. So this is the negative one. This the negative means a lone pair. It's a transposition to this. So this will gain hydrogen first. From alcohol or ammonia, you know, and this is what will happen. What will happen for maximum separation, it will want to prefer at the trans position, and naturally this will take one more electron, take one more electron from lithium, it will become negative, it will get another hydrogen, and the two hydrogen will always be there at the trans position. The reduction eventually gives you a trans product. You know, you can call it an anti-kind of addition, two hydrogen adding, you know, so that the product is the trans product, again because of maximum separation, minimum repulsion, and maximum stability of this radical anion. And this is why it always results into a transalkene. So I think this much is going to help you in all problems based on Birch reduction. I hope this one will help you in all problems based on Birch reduction. This much for the time being. Thank you so much.